So, welcome everyone to the second episode and the second talk of the online seminar on behavior trees in robotics. So this seminar series is targeting the global community of researcher and developer that are working or interested in behavior trees, and especially applied to robotics problems like learning, task planning, control, and whatnot. During these talks, during the series, we will have the opportunity to discuss with leading experts in the field from both academia and industry. I would like to stress one thing, that each episode will be recorded and uploaded on the YouTube. For this second talk, we are lucky enough to have Oliver Biggar as an invited speaker. Oliver is a researcher within the Cicada Lab within the Australian National University. He holds a Bachelor in Mathematics and Statistics from University of Melbourne and a Bachelor with Honours in Computer Science with the Australian National University. His research focuses on graph theoretic methods from gaming AI. And today we will see his talk titled, What Does It Mean to Be Modular? I'll leave the floor to Oliver, and thank you.
Thanks, Mikael. So thanks, first of all, for having me. It's an honor to be here. And my talk is titled, What Does It Mean to Be Modular? And that's kind of a big theoretical question asking about a principle that sort of goes throughout engineering. And so I will make it a little bit more concrete than that. The talk really focuses on two big questions about behavior trees. The first is, why are behavior trees modular? And first of all, it seems like we know that behavior trees are modular because modularity is an intuitive concept, and behavior trees seem to satisfy what we think of as being modular. And they sort of separate into subtrees. We can analyze the subtrees separately. We can modify them. We can sort of build things up and compose them. So in an intuitive sense, we know behavior trees are modular. The idea of this question is to ask why. Can we get any deeper understanding of modularity and why behavior trees seem to have it? In particular, what kind of takeaway essence can we take from behavior trees modularity and sort of apply it to general structures in AI? Now, the second question is also kind of a big question about behavior trees, and at first seems to be totally unrelated. And this question is, which sorts of action selection mechanisms can be represented by a behavior tree? We know a behavior tree has a collection of actions and is a mechanism for sort of switching and choosing between them given the input. But what kinds of actual structures can we construct in this way? And to sort of spoil where we're going with this, we're actually going to find that these two questions are really intimately linked, and that it's by thinking about this concept of modularity that we're able to answer the question about what action selection we can construct in a behavior tree. And kind of in doing so, we get a much more sort of concrete, tangible idea of why behavior trees seem to be modular. And all the stuff that I'm going to be talking about today comes out of a paper I wrote with my colleagues, Mohammed Zamani and Iman Shames. And the full reference is here if you're interested in getting more details about the stuff I talk about, or particularly on the formal verification side, which I'm only very lightly going to touch on today. You should go and check out the actual paper. Now, the kind of general structure of my talk, I'm going to give a very little bit of background on behavior trees. I'm sure you're all familiar with behavior trees, but specifically like what aspects of them I'm going to talk about today. Then I'm going to talk about modularity in kind of a high level way and what seems to be a good definition. Then I'm going to dive into this problem about how we represent behavior trees. I'm going to introduce a concept called a decision structure to sort of be a formal representation of this notion of action selection. And then I'm going to introduce an operation called the modular decomposition on a decision structure. And I'm going to see how this is going to unify these two strands of the talk and sort of identify behavior trees, as well as sort of help us to understand what modularity is. And then I'm going to kind of talk about what we've learned at the end. So to start, we've probably all seen a behavior tree. But here's an example of a very small one. Each behavior tree is composed of a bunch of actions. Each action gets ticked, and when it's ticked, it returns one of three values. Success, indicating it's sort of achieved what it's intended to. Failure, if something that's gone wrong, and running if it's sort of in process. And a behavior tree is a mechanism for composing these using two internal nodes. And we're only going to focus on two in this talk. I'm not going to deal with some of the others you might have seen, like parallel nodes or decorators. I'm just going to keep things very simple and just use two operations, sequence and fallback, to build all our behavior trees. The way these work, a sequence node ticks each of its children from one to the other. And if they return success, it moves on to the next child. If they return anything other than success, then it returns that value, running or failure. And fallback is exactly the same, but the other way around. It ticks each of its children sequentially while they return failure. And if anything returns something that's not failure, then it returns that value. Now, importantly for this talk, I'm going to interpret behavior trees as always being reactive. That is, at each time step, we do this ticking process and we traverse the behavior tree until we find a behavior that returns running, and we select that one. And then come the next time step, we do the entire process again independently. And so really what it boils down to is the behavior tree is a mechanism for checking these return values and coming up with an action to do. And it's just selects that once, and we just keep applying that at each time step. Or we keep checking the new conditions, but each one is independent. The other thing I'm going to assume is I'm going to always treat an action as a black box. I'm just going to give them names like A, B, and C, but I'm never going to dive into what they do. We're always going to treat them as a black box. In particular, for instance, in the behavior trees, we often distinguish between conditions and actions. But a condition is a special case of an action that never returns running. And because I really don't know anything about the actions, I don't know whether they return running or not. So I can't distinguish between conditions and actions. And actually, this is just a simplification. It just keeps everything neat. We can call everything an action. The other nice influence of this simplification is subtrees present exactly the same interface as a single node. This is part of intuitively why we think of behavior trees as being modular, and I'll talk more about it. But a subtree also returns either running, success, or failure when it's ticked. And because of that, we sort of can treat an action as if it could be a whole subtree that we just sort of haven't opened up and looked inside yet. And this is another reason for sort of treating them as black boxes. So the key idea I want to take away is a behavior tree is a mechanism for choosing one of the actions on its leaves, given the return values. Kind of concretely, this behavior tree we saw here before I've got on the right, we could think of it like a selection function, like I've got down below, which selects A if A doesn't return success or failure. It selects B if A returns success and then B doesn't return failure. And it selects C if either A or B return failure. It's important to note that this behavior tree still selects something even if the overall tree returns success or failure. And that's just to allow this to sort of be nested inside another tree and work appropriately. But I'm going to treat behavior trees as essentially being a selection function, just like this one, of choosing an action given those return values. And formally, I'm going to say that two behavior trees are structurally equivalent. And that is sort of equivalent when we're just looking at the structure, actions are black boxes, if they select the same actions, given the same return values to actions, just as I had kind of in that previous function. Now, that's kind of the background. Let's talk a little bit about modularity. Now, we want to know what is modularity, and as good a place to start as any is to look for a definition. So here's one I found in, I think, the Oxford Dictionary, which defines a module as being any of a number of distinct but interrelated units from which a program may be broken into and which complex are built up, or into which a complex activity may be analyzed. Well, it's all kind of wordy, but there's a few concepts that are coming through here. A modular system seemingly is one which sort of breaks into cohesive pieces, or kind of the other way around, can be built up from cohesive pieces. And there is some kind of idea of information hiding, like components only need to know how to use other components and not what's going on inside them. Intuitively, this kind of matches up with how behavior trees treat subtrees and actions identically. In particular, we can sort of think of the different parts and we can analyze or modify them separately. These are all ideas that correspond with modularity. And I've got this diagram here to kind of distill some of these ideas. There are different parts interrelating, and some parts contain sort of internal structure, and the parts outside don't need to know sort of what's going on inside them. This is part of sort of hiding information behind an interface. The best source, I think, for motivation for thinking about modularity is programming, because modularity is such a key part of programming language design, or has been for many, many, many years. Indeed, like a big part of the structured programming movement was forcing people to build programs using a small number of structures. There's kind of function calls, iteration and selection, to kind of, and all these ideas are coming into play. That is, in either a code block or a function call, we can treat a function call in the same way we treat a statement. And it's kind of the same way we treat a subtree or an action in a behavior tree the same. In just the same way, in object-oriented programming, there is kind of a big goal to create cohesive objects, which don't need information of other objects. Similarly, we have processes like subclassing and inheritance in object-oriented programming, where if we use an object, we don't need to know if it's actually a subclass of that class, and so on. And so there's some kind of notion of hiding things behind interfaces and sort of nesting information in a hierarchical way. So we've sort of said some good ideas, but it's good to step back and ask ourselves why we're doing this exercise. Why are we thinking of what we think modularity means? And there's a few good reasons. The first is just, we have an intuition that behavior trees are modular. But if we don't really know why, then we can't use this information very effectively. So for instance, if you gave me something that wasn't quite a behavior tree, had some of the key features, but not others, is it modular or not? I can't necessarily say, because I don't really know what it meant to be modular in the first place. If we are able to kind of think about it for a while, we at least get an understanding. The second reason is that we build theory. Well, if we can get something more formal as a definition of a module, then we can maybe build on top of it and so on. This is kind of just a good idea of why we formalize anything. The third concept, and this is kind of an important one, is if we can distill some of the key aspects of why a behavior tree is modular, then we can apply and understand them to things that are not behavior trees. And then the fourth reason, which is also important, is even while we as engineers may be able to look at a behavior tree, intuitively know that it's modular and therefore design it in parts and work on it in parts, if we want to use automated tools like formal verification or something else that's analyzing our behavior tree, we want those tools to be able to exploit modularity. We want them to be able to sort of work in parts or acknowledge that a change in one part does not cascade. But if we don't know what it means to be modular, we can't really help these formal tools to exploit it. So I think these are good points, but at the same time, we're still totally stuck. We haven't actually gotten any closer to giving some kind of formal intuition for modularity. We've just sort of talked about a lot of ideas. Well, what we're going to do here is we're just going to totally change tack, and we're going to go and talk about that other big behavior tree problem, but we're going to hold on to all the ideas we just talked about because they're going to guide our thinking later on. So let's switch and think about behavior trees as action selection mechanisms. Now, let's come back to this behavior tree we looked at earlier. It's very simple, and we can sort of take out the action selection aspects of it by doing the following kind of reasoning. When we tick this behavior tree, we first go down all the way to the left. And the first node that we tick is A. And we query A and we ask for its return value. Now, if A returns running, we return A. If A returns success, we go and check B. This is what I've got represented as this first arc on the right-hand side of the slide. If A returns success, we check B. If A returns failure, we go and check C next. And then similarly, when we go and check B, if B returns failure, the next thing we check is C. And for all the other combinations, if B returns running or if C returns success, then we select that node and we return that value. So we've actually, with these three sort of arcs, represented all the sort of action switching that's happening in this behavior tree. Because this is sort of another way of representing what's going on. There's a natural translation going from this behavior tree to this representation, but what if we wanted to go the other way? What if I said, actually, instead of if B fails, I want to try C, I want to say that if B succeeds, I want to try C, and otherwise I'll just keep everything else the same. Now, what behavior tree now constructs this desired behavior that I have? All right, I've got these three arcs I have on the left bottom. Which behavior tree corresponds to them? And to kind of, the problem is there actually isn't a behavior tree. There's no behavior tree that gives us exactly these arcs. So this is the statement of our problem. And we can make it a little bit more formal by using the notion of decision structure. A decision structure is a reactive control architecture. So again, it's just a mechanism for selecting an action once, and at each time step it's independent. And it's structured as a directed acyclic graph, and it has a single source. And essentially, the goal of a decision structure is to give sort of finite state machine-like semantics to a behavior tree. So the way a decision structure does its action selection is we start at the single source, in this case, A, and the decision structure on the right. And then we tick it, we ask for its return value. If A returns success, we follow the arc labeled S and we go to B. And then we query B, and if B returns failure, we follow the arc labeled F, we get to C. And similarly, if we queried A and we got a failure, we follow it to C. And if at any point we query the node and the return value it gives us doesn't match any of the arcs, then we select that node and we return that value to the overall structure. And this translation I have here is just sort of very natural from behavior trees to decision structures. And in fact, it's not just natural. We can prove that it preserves structural equivalence and it's unique up to structural equivalence. This is the way to translate a behavior tree to a decision structure. So now we've got this sort of natural way of embedding the sort of world of behavior trees inside a larger space of reactive architectures that is all the decision structures. And before we couldn't answer this question of what things aren't behavior trees because they lived on their own. Now they live in a bigger space and our problem has become completely precise. The question is, which decision structures are structurally equivalent to a behavior tree? Which things are in this oval on the right? That is the formal statement about our second big question. Again, we kind of don't immediately have a way to progress, but the idea we're going to use is to all our thinking we had about modularity. And the key thing is we're going to look for a way of grouping nodes in a decision structure. And our grouping is going to be based around having what we're going to call a common interface to the rest of the graph. Now, this approach is actually inspired by an operation on graphs, which has existed in the graph theory literature for a while and is suggestively called the modular decomposition. So it seems to be getting at kind of the thinking we're thinking about. And it centers around the definition of a module, which in a graph is a set of nodes where every node outside of that set is adjacent to either all the nodes in here or none of them. So as a concrete example here, in this graph, the set of nodes 5, 6, and 8 together are a module. Because for every other node, like 4, it's adjacent to either all those nodes or none of them. There's no node that's adjacent to just some of them. In other words, they share sort of the same interface with every other node in the graph. It turns out modules allow for this recursive nested decomposition of a graph, as we've got here on the right. We've turned this sort of graph into like a graph which has graphs embedded in its nodes. And this hierarchical representation actually has preserved all the information of the graph, and it's very useful for some graph algorithms. And it's turned it into this sort of hierarchical thing where the information inside is sort of hidden behind an interface. It seems to be meeting a lot of our criteria of being modular. And we're going to try and apply the same thing. But to do that, we're going to need a definition of a module and a decision structure, which is not going to be exactly the same because the information we need to preserve is not the same. We'll see later why this is the right definition. But for now, we're going to say a module in a decision structure is a set of nodes that has 2 properties. The first I'm going to call having one entrance. What that means is all the arcs going into our set of nodes have to go to just one node. And all the nodes within our node have to be reachable from that one in our set. The other property we're going to ask for is that for each of the return values that we have on our decision structure, if there is an arc out of our set with that return value, then within the set, every one of those nodes has an arc with that label. And if it leaves the set, then it has to go to that same node. A priori, this definition seems pretty obscure, but the best way to look at it is really to just look at an example. Now, the intuition here, before we go through each of these cases, is that a module should be something that preserves the information in the original graph if we treated it like a single node with the contents of that set inside it. So we're trying to think of this as like, we're going to collapse the set A and B into a single node, and then we're going to nest inside them the structure that just consists of A and an arc to B. And we're asking, when does that not lose any information, right? We want this kind of nested representation. Well, figure 1 isn't going to work. It can't be a module. The reason is because the arcs going into it, into A and B, the set we want to be a module, go to 2 different nodes. So if we treated them as a single node, we would lose the information of where we start. In figure 2, we've got sort of, let's go to figure 3, because I think it's a bit easier. Here we've got all the arcs into the set go to the same place. They go to A, and B is reachable from A. So it seems like it might be a module on the way in. But the problem is, if we leave this node, this sort of super node combined with A and B with the value F, we don't actually know where we should go because it depends on what node inside. So in other words, there's 2 F exits, and so we can't treat this as a module. The third case, the reason why this isn't a module, even though it has a single exit for both S and F and a single entrance, is that A has no F arc. This means information would be lost because if we got to A and A returned failure, then we select A and the whole structure returns failure. That information is lost if we collapsed A and B to being a single node. And so finally, for A and B to be a module, we need the cases we've got here in figure 4, where there's one way in to A, and then A and B, there are exits on the values S and F, but they both go to one node respectively, and both A and B have arcs corresponding to S and F. As some kind of like motivation we had from these like module thinking we did earlier, this is very simple to like, similar to thinking about a function call. We want to essentially have a node, which is like a function call to another decision structure, which contains A and B. And so we need to sort of, the function goes in from one point, that's the start point, and comes out where we subsequently go after the function depends only on the value returned by the function. Likewise, it's also kind of motivated by the idea of method resolution in a subclass in object-oriented programming, which is when we're inside this sort of nested node, and one of our nodes returns, say, success. We first check if it has a success arc within this node. If it doesn't, we sort of zoom out, and then we see if our sort of nested node has a success arc, and we follow that. Modules, just as in the graph case, and this is kind of why it turns out they are the right notion of module, also have this recursive decomposition of a decision structure that is essentially unique. This is the kind of non-trivial maths of the result, and it allows us to sort of break down a decision structure into this kind of nested sequence of decision structures. So here, we start this process by just finding the largest modules. And here's what they are in this case, on this decision structure. A and B is a module, and C, D, F, G, H, I is also a module. So then what we're going to do is we're going to turn this into a decision structure with 2 nodes and a single F arc between them, with the A, B nested in the first node, and the C, D, E, F, G, H, I nested in the second node. And the fact that this is sort of equivalent and we can still get the original out is because the modular decomposition works. And we can do this recursively. Turns out this second node, which is still quite kind of large and complicated, can actually be broken into more modules. Here's a maximal module inside it. And again, we're just going to turn that into a nested decision structure, which is just C and then an S arc to another node, which has a decision structure nested inside it. And we repeat this process. Like there's more modules inside, there's still more modules here. And eventually we get here where there's no more modules left. And we have completely broken this decision structure down into a hierarchical nested sequence of decision structures. And actually each of them is very simple. Each decision structure in this here is a path with just sort of other paths nested inside nodes. Now this is where kind of our 2 streams start to come together, which is it turns out this modular decomposition operation is exactly what we need to answer what is a behavior tree in the decision structure. Turns out a decision structure is equivalent to a behavior tree if and only if every one of these decision structures in its modular decomposition has a path structure. In fact, just as in this case, right? It breaks down to be the simplest possible, which is everything is just a path. Then it's a behavior tree. So it's not just that behavior trees break down into many pieces, which kind of intuitively makes sense because we know that they break down into subtrees. It's actually anything that breaks down into pieces that are really simple is a behavior tree. And actually, in this case, the subtrees of the behavior tree are in a one-to-one correspondence with the modules of the decision structure. So modules are sort of capturing that idea of being a subtree. To kind of show you how we can sort of demonstrate this, this is this nested decision structure we just constructed. And because every module is a path, it should be equivalent to a behavior tree. But which behavior tree? Well, we can construct it just by going from outermost in. The outermost structure here is two nodes with a single F arc between them. We're going to turn that into one fallback node, which I'll just write as F for now, and two children. And then we're going to apply this thing recursively. So we get over here, we've got A and a single S node to B. That'll become a sequence node with two children, A and B. And likewise going on over here on the right, because at each point, it's just a path. So we're just going to put the children in order in the path, and the label on the path will become the behavior tree node. And we repeat this, and we've constructed this behavior tree where I've used S and F for sequence and fallback, just to make it nice and clean. And if you go and check the translation back to a decision structure from this behavior tree, you will get the decision structure that we started with. Now, it's good to kind of think here, like this has told us what happens, like we've identified behavior trees. And we know that modules in a decision structure is the same as subtrees of a behavior tree. Well, the nice thing about this is that modules exist even in decision structures which aren't behavior trees, so don't have a tree representation. You've sort of generalized the notion of being a subtree. And now we can ask the question, how close is the structure to being a behavior tree? And the mechanism we're going to do this actually also comes out of our sort of modularity thinking. It's a measure which was constructed for the structured programming literature called cyclomatic complexity. And it's really just counting sort of how much a control flow graph in program branches. So how much branching is going on, because that's what kind of causes complexity. And in particular, something has cyclomatic complexity 1 if it's a path, and everything else has more complexity than that. It's constructed using this formula. But the key idea that came out of this original paper in the structured programming literature was actually the complexity of a program should be the complexity of its most complicated function call. And in the same way, we're going to say that the essential complexity of a decision structure is the complexity of its most complex module. And so if all the modules break down into really simple structure, then the essential complexity is very small. In particular, if all the modules in the decomposition are paths, then the essential complexity is 1, because every module has cyclomatic complexity 1. And from our earlier theorem, this is again a characterization of behavior trees. A behavior tree, a decision structure is a behavior tree if and only if its essential complexity is 1. So we sort of talked about a lot, but I think it's important to kind of summarize what we've actually found. First, we solved one of our problems, right? We identified which decision structures are behavior trees. And in doing that, we kind of got some intuition to why. It's because that they are built from two operations, which are constructing paths and then nesting paths inside paths. And this is what the modular decomposition told us. There's an algorithmic side to this. We can quite efficiently compute the modular decomposition, and consequently, we can check, given a decision structure, if it is or isn't a behavior tree. The second point is, by discovering this kind of generalization of a subtree that is a module, we have like pulled out the modularity, the notion of modularity that behavior tree subtrees had. And it turns out, I mean, I didn't talk about it here, but we can use modules in that same way. If we make a small change to a module, it doesn't cascade. And formal verification actually can take advantage of this if we sort of make changes periodically. This was kind of the second half of the paper that I didn't talk about, but it works just as well in modules as it does for subtrees of a behavior tree. The third kind of bit of intuition we got is explaining why behavior trees are always kind of quite readable and well-behaved. And it's sort of because they're built from just nesting and sequencing. So if we thought of them as programs, it's like a program that is built only from function calls and sequences of statements. Each function body is a sequence of statements that might consist of more function calls. This is how behavior trees are built. And so they can never sort of get messy. We can always read them. But the particularly important part about all of these, because these are all ideas we sort of knew, is we can generalize all of these things beyond behavior trees now. In particular, using this essential complexity notion, we can say how close a structure is to having a tree representation, that is being a behavior tree, which means suppose we had a big behavior tree. We want to change one thing. We want, for instance, after we check this action, if it returns success, instead of going to this action, we want to go to a different one. The result may or may not be a behavior tree. But if it isn't, we can at least look, what does it do to the complexity of all the modules? What is the impact? How sort of close is it to being modular? As another thing, we can use these ideas even when we're not using behavior trees to try and keep complexity minimal. So if we're using, for instance, finite state machines, while they have this hierarchical representation, it's already established in the finite state machine literature that you can nest them and so on. The problem is it's not really strictly enforced. There's nothing stopping you from creating arbitrarily messy finite state machines, even if we use this nesting. But now we can use the same idea of enforcing that each part is sort of bounded in complexity, and then using the nesting idea to create finite state machines that are quite well behaved. I mean, to do this, you sort of need the right notion of a module in a finite state machine, which is very similar to this, but a bit different. So actually, after I finished this, I spent a lot of time thinking about this problem. If you're interested in that problem, I have another paper on it. But this is, yeah, it's very, very similar to this, actually. The ideas came out. Anyway, that's pretty much everything I wanted to talk about. So I'd love to hear if anyone has any questions.
Thank you very much, Oliver. It was a really great talk. So I asked the participant to raise a hand in Zoom if they want to ask questions. Thank you. So we have a question from Jacek Malik. Jacek, please.
Yes, hello. Thank you very much for a very interesting talk. I really liked it. I've got a couple of, well, maybe questions, maybe comments. First of all, I'd like to understand the concept of decision structure. If you have on slide 6, you have given a very simple example. There you have the idea that, well, behavior tree is translated into the structure. Then we have those dependencies. If A is false, then C. If A is true, or if it succeeds, then B. So instead of true, false, you have succeed, failure, which of course means that you have semantics associated with A and B and C. There is something happening underneath there, which in a sense you neglect, but it is there. But what I want to ask is whether they are deliberately incomplete. Because what happens if B succeeds? So, of course, from the behavior tree point of view, this is the outcome. This is the result. This is the, but from the logical point of view, this is an incomplete specification of it. So, what do you have any comment on that?
Yes, it's totally deliberately incomplete. The reason why it's actually sort of good that it's incomplete is because it makes the nesting well defined. It's because if it's not handled here, this is when, if this was nested, it would be handled at a higher level. In the same way, considering this behavior tree, if B succeeds here, then the whole behavior tree succeeds. Well, if we're looking at it in a modular way, then when we look at this subtree, we sort of aren't supposed to know if it's actually a part of a much larger tree. And if it is a part of a much larger tree, just saying the tree succeeds is great. I mean, we come out of this and then we'll follow the arc to somewhere else. You know, the success will be captured somewhere else in the tree and we'll move on, or maybe we won't, but we don't need to know because it's modular. So in the same way here, yeah, if B returns success in this decision structure, then the whole structure, just like the behavior tree, just the structure returns success. And if this structure were nested inside something, then we would sort of follow the success arc of that. But
okay. Yeah. Okay, so you can, there is a way of making it complete in this sense. Perfect. Then what I noticed is that modularity concept that you introduced a bit later. It was slide 20. Reminded me very, very strongly about the state charts of David Harrell as they were originally introduced. So this is very similar idea, and I suppose you are aware of it, of course. But do you have any comment on that? Are there differences? Let's put my question this way.
Yeah, I mean, they are really very similar. I mean, in fact, the main difference in this case is that decision structures have a slightly different semantics to finite state machines. But in the follow-up work, when I focused on finite state machines, in fact, the exact goal was to basically do the converse construction to like Harrell's state charts. Mm-hmm. So in the state charts, it's like at design time, we build in the hierarchy.
Yep.
So the question is, if the hierarchy wasn't there, you know, you're given a finite state machine with no nesting, can we pull it out? Can we look at where nesting could have been equivalently? Because we can take a nested, you know, state chart and get rid of the nesting by sort of flattening it out and putting the missing arcs in. So the goal of this in decision structures and subsequently my work in finite state machines was, could we discover the hierarchy?
Yep.
You know,
yeah. Yeah, so I think this is a very, very interesting point in your work, this creation of this hierarchy and modularity. I like it very much. So I'm looking forward to checking or looking at your papers. Thank you.
Thank you.
Other question, Peter?
Yes, thank you, Oliver. Excellent talk. Well done. So my question is, so in early behavior trees in the gaming community, most people used the memory sequence, whereas there's also the memory-less sequence, which I think is kind of should be the standard. But obviously your whole theory here relies on memory-less nodes. So could you comment on that?
I mean, yeah, there's I assumed everywhere here, yeah, that everything is memoryless. It's a mechanism for, you know, you go through the ticks, you select an action, you're done. Next time, we're not storing anything extra. I mean, and part of the reason is because, yeah, I mean, because you could do it. You just need to like adjust the syntax, you know, appropriately. Later, as I talked about, did work on finite state machines, and they do have memory. So there's nothing structural there about the memory, but it does make the semantics different, which means you have to check different things when we're asking if this is a module, because there's different places where the information should be stored. Like the key thing for getting the module definition right is making sure that no information is sort of gained or lost when we do the nesting or undo the nesting. So I don't know exactly how we would do this representation, how we would represent the sort of stored internal value in a memory sequence of where we're up to in the sequence. It's a complicated question. I mean, and mostly I avoided it because one, I do think this version is much neater and it made it possible to sort of progress. Probably, you know, with enough added sort of mess, you could fit it in.
Thank you. Yeah, I totally agree. I think these memory nodes, it's like having functions with internal variables. So it kind of creates complexity that you don't want, but some people like them.
Yeah.
Thanks.
Thank you. Are there other questions from the audience? Give you some seconds to think about it. So if there are no other questions, we thank again the speaker and all of you guys for joining.
you.
And thank you, and we'll see you in the next episode of the series. Thank you, everyone.